Kia ora koutou, no mai, haere mai. Welcome to lesson 26 for introductory physics. This lesson is continuing on our idea of atomic structure. This time we're going to look at nuclear decay. So we talked about the idea that atoms are made of a nucleus surrounded by electrons, and that nucleus is made of protons and neutrons, but those nuclei can change. They can decay spontaneously. So we talked about them forming in stars. That's when we push them all together and the star creates new, heavier elements. But once an element has been created, some of them are not stable and they will decay. And that's what we're going to look at here. So first of all, we're going to talk a little bit more about that strong force that does hold the nucleus together, holds all those protons and neutrons together. And that will lead us into discussing alpha and beta decay, which are types of radiation. And we're going to talk about the effect that those types of decay have on the atoms as they occur. We're going to look at decay equations. We're not going to get too into detail on these. We're going to keep it fairly simple, but we will look at decay equations. We're going to define and introduce the term half-life and talk about what that means, and also how that half-life of different elements can be used in processes called radiometric dating, the most common of which is called carbon dating, which you may have heard reference to. So that's our goal for today. It's all actually about radiation because this is what goes on in the nuclei of atoms. So the strong force. We mentioned this already, that very strong force that holds all of the nucleons. Remember, nucleon means proton or neutron. Anything found in a nucleus is a nucleon. So the strong force holds all those nucleons together. It was imaginatively called the strong force. We decided, well, it has to be very strong to overcome that electric repulsion. Remember, all the protons are repelling each other. It has to be strong to overcome that, so we'll just call it the strong force. I didn't get a say in that, obviously. It does actually exist between the quarks and gluons that make up the nucleons, but we're not going to go into that again, just mentioning it if you are interested at all in that aspect of physics. So all the neutrons and protons within a nucleus are attracted to all the other neutrons and protons by the strong force. So that strong force is what's holding it together over and above this electric repulsion that we get. But the strong force behaves a little bit differently from other ones that we're used to. It has its strongest attraction when nucleons are about 1.3 femtometers apart. That's 1.3 times 10 to the negative 15 meters, femtometers. If they get too close, then the strong force actually becomes repulsive. It won't let them get too close. You can, again, think of it like a spring. Springs are quite a useful visual analogy for a lot of things. So as the nucleons get too close, they're like compressing the spring, and so it pushes back. So the strong force acts a little bit like a spring in that region. There's a really strong attraction when you pull it out to 1.3 femtometers, and if you push it into less than half a femtometer, then it will try and repel it. But the way that the strong force differs from other forces we've looked at is that if the nucleons get further separated, they go beyond that strongest attraction point, then the strong force actually decreases again. And by the time they get more than a couple of femtometers apart, then the strong force has dropped all the way to zero. It looks something like this. This is not to scale. You'll notice there's no numbers on the vertical axis. It's just a rough guide for you to hopefully visualize that force. As I said, though, the strongest point is around about 1 and a bit femtometers, and that is pretty accurate. That's pretty reliable. Remember, the protons are all repelling each other throughout all of us. The electric force that we're going to discuss more next, I've said next week there, it probably will be next week when I put the lesson up, but it is next section anyway. It's only between protons, not the neutrons. Neutrons have no electric charge, so they don't experience this electromagnetic force. It's always repulsive because the protons are all positive, and it is inversely proportional to the nucleon separation. So it's kind of like gravity. The closer they get, the more effect that force will have. So when they get really close, the electric force is going to be strong, and remember, it's repulsive. As they get further apart, the electric force drops off and it becomes weaker. But it's a curve. It's a square law, so it's going to have that square law curve, and it will look something like that. We've added that pink line for the electric repulsion between protons. Remember, that's only between protons. That strong force is between any nucleons, both neutrons and protons. So we've got these two different forces occurring at the same time. Again, there's no scale on that vertical axis. Just look at the shape of the curve. Don't worry exactly about their magnitudes. It means if you have two protons, they will be repelled if they're too close, because if they get less than half a femtometer-ish, then both the strong force and the electric force are repelling. The electric force gets very strongly repelling as you get closer, as does the strong force. So if you get too close, protons are very strongly repelled. But there's this region where the strong force actually outweighs the electric force, and the protons will be attracted to each other. They're still experiencing repulsion from the electric force, but they're experiencing a greater attraction from the strong force. So between around about 1 and 2 femtometers, we have an attraction between two protons rather than a repulsion, as we might naively expect, just taking into account that electric repulsion. I've drawn that net force on as a black line on that diagram. Again, very approximately, it's just to give you an idea of the shape of it. So you get repulsion if you're too close, this region of attraction, and then once you get beyond a certain point again, the strong force drops away to pretty much nothing, and the electric force, even though it's weaker because the protons are getting further apart, it's still there, and it's still significant. So we do have to take that into account. So we actually have repulsion at close distances, repulsion at further distances, and just the sweet spot where they will be attracted to each other. If you've only got a few nucleons, then they'll all stay about a couple of femtometers apart, and they will be strongly attracted to each other, and the nucleus will stay all connected to itself, even though you've got these protons repelling. As per my little diagram there, we've got lithium with 3 protons and 4 neutrons, and the protons are all repelling each other, but the neutrons are all strongly attracting, and actually the protons might still be in range to be attractive as well. It's hard to know from my crude drawing, but regardless, we've got a lot of attraction overall and only a little bit of repulsion because we've only got the 3 protons, but there are 7 nucleons in total, which are all strongly attracting. So when there's only a few nucleons, pretty stable, everything's pretty happy, the attraction is going to be much greater than the repulsion. As we add more nucleons though, they are each strongly attracted to their neighbors, which is great, but every time we add a proton, it's only attracting its nearest neighbors, only the ones within a couple of femtometers. And that's the nearest 1, maybe 2 nucleons on each side. If you add it to a big nucleus, there are protons throughout the whole nucleus that are all going to be repelled. Remember, that electric force drops off, it gets a bit weaker, but it's still there and it's still very much significant right across the distance of a whole nucleus. So if you take a nucleus that has maybe 20 protons and maybe 30 neutrons, and you add a proton to the edge of it, it'll attract all of the protons and neutrons right next to it, but it's going to repel every single one of the other 20 protons that are in the nucleus. So it's adding some attraction, but it's adding a whole bunch of repulsion as well. So as you get bigger and bigger, at 20 neutrons, not too big a deal. 20 protons, not too big a deal. By the time you add a proton to a nucleus that already has, say, 100 of them, you're now only adding a little bit of attraction compared to how much repulsion you're adding, because you're repelling every one of those other 100 protons. So as we get bigger nuclei, you can imagine we're getting more repulsion with every proton we add, so we have to add more and more neutrons for every proton. So you cannot have a nucleus with lots of protons without having lots of neutrons. It just won't work, right? There's too much repulsion, it will break apart. So that's what happens, and as we saw with the mass numbers in the previous lesson, you can get different numbers of neutrons because it doesn't matter exactly how many there are, we just need a whole bunch of them in order to act as that glue to overcome that electromagnetic repulsion. If the electric repulsion is too strong, if there are too many protons and not enough neutrons, and the strong force can't hold it all together, the electric repulsion wins, then the nucleus will split apart, destroying the atom. But there are a few different ways it can do that. To start with, let's look at just a single neutron. I know we've been talking about repulsion between protons, but we're actually just going to talk about a single neutron to start with. A single neutron on its own, not in a nucleus, just flying around the universe on its own, is actually unstable. Unstable means that it won't continue to exist in its current form. What a lone neutron will do is eject an electron. It will just throw an electron out into the universe, and as it does so, remember that an electron is a negative charge that will leave the neutron with a net positive charge. It turns it into a proton. So a neutron can spontaneously eject an electron and turn into a proton. And that's what it will do if it's just on its own out in the universe, not part of an atom. And this is called neutron decay. So neutron decay is a neutron turning into a proton and emitting an electron. While it's less common in a nucleus, it can still happen. And it happens if there are too many neutrons in general, not a strict rule, but in general, if there are too many neutrons, so far more than you need to hold all of the protons together, then one of them is quite likely to turn into a proton, to eject an electron and turn into a proton. And that will change the number of protons and the number of neutrons, but keep the overall mass number the same. And this is called beta decay. So a nucleus emitting an electron and the nucleus changing as a result. We've now got one more proton and one fewer neutron. That is called beta radiation or beta decay. The ejected electron is called a beta particle. Now, a beta particle is just an electron. That's all it is. It's just an electron, but it's a highly energetic one that's being emitted from a nucleus. So if an electron is highly energetic and it's just been emitted from a nucleus, that's when we can call it a beta particle. So you can't call every electron a beta particle, just the ones that result from this beta decay. During beta emission, as I said, the mass number hasn't changed. A neutron is turned into a proton, but both of those count for the mass number. They both still add one atomic mass unit, almost, depending on the element. They add one atomic mass unit to the atomic mass, the mass number, not the atomic number. But the atomic number has changed because the neutron didn't count before it decayed. It wasn't part of the atomic number, but once it turned into a proton, that now does count for the atomic number. So the atomic number has increased by 1, even though the mass number hasn't changed. But that means the element has changed. So beta decay will cause one element to turn into another. It'll turn into one with an atomic number of 1 greater than it started with. A common example is carbon-14. Carbon-14 starts with 6 protons and 8 neutrons. Carbon is the 6th element, so even if we didn't know that breakdown, saying carbon-14, you should be able to look at that. I don't expect you to memorize that carbon is number 6, but if you looked up that carbon was number 6, then you would say carbon-14 must have 6 protons, therefore 14 minus 6, we must have 8 neutrons in order to make that mass number 14. One of those 8 neutrons can decay. Carbon-14 is radioactive, it can decay. So one of those 8 neutrons can decay and emit a beta particle and turn into a proton. That means we now have 7 protons. We've still got mass number of 14. There are still 14 nucleons, 14 things inside the nucleus. But where we had 6 protons and 8 neutrons, if you turn one neutron into a proton, you've now got 7 protons and now only 7 neutrons left. So that becomes a nitrogen-14 atom. So it's still 14, still mass number 14, but we've gone from carbon, which has 6 protons, into nitrogen, which has 7 protons. Because writing that all out in words, as we just did, is not very efficient, we have come up with decay equations. Decay equations use the atomic symbols, so a big C for carbon, a big N for nitrogen, and we also use the lowercase e for electrons. So remember, a beta particle is just an electron, so we write that as an E. But what we do when we write the decay equations out, as I've done here, is we write the mass number along the top. So 14C becomes 14N, as we just said. We also include the atomic number on the bottom. So we've got 6 for our carbon, that becomes 7 for our nitrogen. And remember, the atomic number is just the count of protons, and protons all have a charge of +1. So we include electrons and we give them an atomic number of -1. They cancel out a proton, essentially. Because remember, we're only talking about the nuclei of the atoms here. We're not talking about the electrons that orbit them. We're only talking about the nucleus. And in the nucleus, we had 6 protons, and then we have 7 protons, and that means we must have lost we must have emitted a negative charge, and that is 1 electron, 0, -1 E. When you write these decay equations, your job is simply to make sure they balance. We go across the top with the mass numbers and we check that the mass numbers all balance. Carbon 14, nitrogen 14, they both have mass number 14. The electron has no mass. Remember that its mass is really tiny compared to the nucleons, about 0.05%, I think it was. So the mass is tiny, we ignore it. It's negligible for our purposes. So we can add that up. 14 equals 14 plus 0. That's perfectly balanced. On the bottom, we do the same thing. 6 equals 7 minus 1. Again, perfectly balanced. So that decay equation is balanced. If you were asked to complete that, we might, for example, leave the electron space blank and ask you what is emitted in this equation. And you would just look at the equation. You'd say 14 at the top, 14 at the top. Therefore, we must have something with no mass being emitted. So already you should know it's an electron. Then you can check the bottom and go, we've gone from 6 up to 7. So 6 equals 7 minus 1. We would have to add a minus 1, and that again agrees with it being an electron being emitted. So it's quite easy to balance these equations once you know what can go in there. So that's a decay equation. They are pretty straightforward. There are a bunch of them on the worksheet, I believe, for you to have a practice of. In reverse, it can occur, that is where a nucleus captures an electron and turns a neutron into a proton. It's known as electron capture. We don't normally discuss this much in the course. I just wanted to mention it for those of you that were interested. It can occur back that way. So a nucleus can catch an electron. Then we can do that in labs. We can fire electrons at high speeds into a nucleus, and then the nucleus will absorb it and turn a neutron into a proton. Sorry, other way around, turn a proton into a neutron. It doesn't normally occur with the same elements that would experience beta decay. So 14 nitrogen 14 wouldn't normally capture an electron and become carbon 14. It doesn't normally happen that way. It certainly can, we could force it to, but it's not what would normally occur. So the beta decay occurs when there are a few too many neutrons. They're not all really needed to hold the nucleus together. One of them might go in decay and turn into a proton. On the other hand, if you've got too many protons and not enough neutrons to hold them, to glue them all together, then the nucleus can sometimes just emit a little cluster of them, or just get rid of a couple of protons. It's always 2 protons, and they always take 2 neutrons with them. And so we just get rid of 2 neutrons and 2 protons. That process is called alpha decay, and the emitted cluster of nucleons is called an alpha particle. You'll notice that it's 2 protons and 2 neutrons, and that's the same as a helium nucleus, so we sometimes just call them helium nuclei rather than alpha particles. They're the same thing essentially, but as with the beta particles are electrons, but they're only beta particles if they've just been emitted by a nucleus. Same thing here. If we've got this emission of a helium nucleus by a bigger nucleus, then it's an alpha particle. You can't go and call any helium nucleus an alpha particle. So an alpha particle is a helium nucleus. As with beta emission, alpha emission also results in a change of element. It must. It's changing the number of protons in the nucleus. It's not possible for it to still be the same element afterwards. In this case, the nucleus has lost 4 from its mass number and 2 from its atomic number. So it has changed in both mass and atomic number, but the decay equation process is exactly the same. We write the atomic symbols down. In this case, we've got U for uranium, TH for thorium, and it's emitting an alpha particle. As with the beta particle, we wrote electrons for beta particles. We wrote a little e. For alpha particles, it's pretty common to write helium, so He. But again, we just balance the equation, exactly the same process. 238 is equal to 234 plus 4, that balances. 92 is equal to 90 plus 2, that all balances. So we should be happy with that decay equation. And again, sometimes you'll be given a decay equation with some elements missing. So we might not put in the thorium term in this equation. You might have to figure it out. So you'd look at 238, you'd see that the helium or alpha particle has a mass of 4. So whatever particle we're left with, whatever atom we're left with, it must have a mass of 234 in order for that equation to balance. So you can just work through those equations in that process. Alpha decay isn't quite reversible in the same way that beta emission is, but we can certainly cause them to collide. We can fire a helium nucleus at another atom and cause it to collide with the nuclei of that atom, but it won't usually just absorb the whole nucleus. What will usually happen is that it changes and emits something else, so it breaks into 2 new different things. For example, if you fire a helium nucleus at a nitrogen 14 atom, then what you'll often get is an oxygen 17 and a hydrogen nucleus. So you'll get 2 new different things, but you won't just get one big atom. So those two processes, alpha decay and beta decay, they are both types of radioactivity, but there is a whole bunch of terms around radioactivity, so we're just going to take a moment and think about the different words. Radioactive decay is talking specifically about the processes of alpha and beta decay. A nucleus emits high energy particles, either a beta particle, which is an electron, or an alpha particle, which is a helium nucleus. It emits high energy particles and changes into a different element. That always happens. It must change into a different element. If a neutron turns into a proton, you've now got one more proton than you had before. That's a different element. If a nucleus emits an alpha particle, you've now got two fewer protons than you had before. That's a different element. So the element will always change. Nuclear radiation is a term we use to describe the emissions from radioactive decay. We also just use the term radiation sometimes, but we also have the term radiation when we're talking about thermal physics, and we'll meet that again when we come back to electromagnetic radiation or light, which is similar to what we had in thermal physics. So sometimes we'll put nuclear in front of it just to be really clear that we're talking about nuclear radiation. We're talking about these alpha and beta particles that come out of nuclei as they decay. Radioactive as a term is simply the name we give to any particle which is capable of spontaneously undergoing radioactive decay. So any atom whose nucleus is likely to give off an alpha particle or a beta particle and decay, we call that radioactive. And radioactivity is just a blanket term for all of this stuff, for radioactive decay and the resulting radiation and the particles, everything, all of it, we just call it radioactivity as a blanket term. Another term, transmutation, is one that you probably don't necessarily need to know. It's perfectly acceptable to just say that one element changes into another, but you can also use the term transmutation. So transmutation means changing one element into another. It's kind of an odd word, transmutate, right? It's mutating from one into another, mutating change, mutating transmutation. So that's all it means. It occurs constantly in the natural universe. It's always going on, as we just saw. These particles just decay. They give off alpha and beta particles and just change. And that's actually just happening all the time, constantly. But we can, of course, artificially initiate it inside laboratories as well. As I mentioned, you can fire a helium particle into a nitrogen nucleus. If you do that and you get an oxygen nucleus and a hydrogen nucleus out, then you've changed the elements. You have changed nitrogen into oxygen through firing a helium nucleus at it. So we certainly can do that. The helium nucleus must be really highly energetic. You have to have a highly energetic alpha particle, and usually the best source of those, the best source of highly energetic helium nuclei is alpha particles, ones that have just been emitted by other nuclei as they decay. So you use them changing of one element into another to then force another element to change as well. So that's artificial transmutation, is where we sort of guide it and force it to happen. But it is happening all the time, everywhere throughout the universe anyway. As we saw, neutrons are responsible for beta decay. One will spontaneously change into a proton and eject an electron. So that neutrons are already responsible for part of what we're looking at. They're also involved in alpha decay, as the two that are emitted with the alpha particle are obviously making up mass numbers from either side. So there are neutrons involved there, but neutrons are also relevant in that usually when we get alpha decay, we're getting rid of a couple of protons because there aren't enough neutrons. So it's a lack of neutrons that will generally cause alpha decay. So protons might determine which element an atom is, but the number of neutrons is very relevant in determining its radioactivity. It's not a hard and fast rule. There's no strict laws that we can write down and learn to figure out if an element is an atom, a specific isotope is going to be radioactive, but neutrons are definitely very relevant. Too many of them, one is likely to turn into a proton, change the element, and not enough of them, the element is likely to give off an alpha particle and change into a different element. So neutrons very relevant for radioactivity. We've already met the term isotope for elements of the atoms of the same element with different numbers of neutrons. Any isotopes which are radioactive are simply known as radioactive isotopes. We often refer to non-radioactive isotopes as stable isotopes. Remember, stable is It's the same word as we have in everyday life. It just means not going to change, not likely to change. So stable is quite happy to just sit there and not be affected, not change in any way. Stable isotopes are the same. They won't undergo radioactive decay, whereas radioactive isotopes obviously are the ones that are likely to. As I said already, that's often dependent on the number of neutrons. If you don't have enough neutrons, then you're likely to be radioactive. If you have too many, you're likely to be radioactive, but there's a region in the middle where you're likely to be more stable. So the number of neutrons is relevant. For example, xenon. Xenon is the 54th element. It has 7 stable isotopes: xenon 126, 128, 129, 130, 31, 32, and 34. Other isotopes can exist. Sometimes they do naturally, sometimes we have to create them in a lab, but they are usually, they are all unstable or radioactive. Any other isotope that can or does get created is unstable and will decay. It might decay very quickly or it might take a long time, but it will decay. So you'll notice that there are some there that are stable, whereas ones in between aren't. So 126 and 128 are stable, 127 is not. So it's clearly not a strict rule of this doesn't have enough neutrons, so it's going to decay, and this does, so it won't, because we have interesting things happening like that. Xenon 126 being stable, and 127 not being stable, and then 128 being stable again. So, as I said, there's no hard and fast rules, no laws to memorize. Generally, we'll just go and look it up. There are reference tables. Even Wikipedia is actually great for checking elements and looking at the stable versus unstable isotopes, as well as what kind of radioactivity they undergo. The isotopes with fewer neutrons aren't stable. They will undergo alpha decay and emit a couple of protons in the form of a helium nucleus. So 125 and 127 both undergo electron capture to turn into the 53rd element, iodine. Xenon 124 actually undergoes double electron capture. So that in that case they actually won't. I misspoke when I said they'll capture and emit an alpha particle. This one will absorb an electron, so it's still getting rid of a proton, but it's doing so by turning it into a neutron. So in this case, it'll absorb an electron, turn into a neutron, and go down into iodine. Xenon 124, as I've noted, actually undergoes double electron capture, but again, we're not really going to get into that. We're focused more on the radioactivity, the emission of particles. Xenon 133 and 135 have more neutrons, and they do the opposite. They experience beta decay, turning one neutron into a proton. So xenon does the electron capture and electron emission. Xenon 136 undergoes double beta decay, and that's exactly what it sounds like. 2 neutrons turn into protons instead of just one at a time. So there are different types of decay. Different isotopes will undergo different types of decay most commonly, but there's, actually I'll leave that. I was about to add another comment about different types of decay from the same isotope, but we mentioned that shortly. Decay chains. Often a radioactive particle will undergo radioactive decay and produce a new radioactive isotope. And so then that will undergo radioactive decay and produce another element or atom or isotope. But often that will be radioactive as well, and it will continue. And sometimes these chains, these decay chains, which is just where one atom decays into another radioactive atom, sometimes these chains can get very long, as per this one, uranium-238, I've done the heading wrong, it is 238. Uranium-238 decay chain. Uranium-238 emits an alpha particle, it becomes thorium-234, that's radioactive, it emits a beta particle, that becomes protactinium-234, which also emits a beta particle to become uranium-234. And we're back to uranium, but a different isotope. That isotope will also emit alpha particles and so on. I'm not going to read every row out, we'll be here for ages. And so you can follow that path through, and every step of the way is just one of the alpha or beta particle decays that we have seen. And eventually it gets down to thallium-206, which emits a beta particle and becomes lead-206, and lead-206 is stable. So once it reaches lead-206, then it will remain as lead-206. In natural circumstances, we could go and encounter lead and force it to do something else, but naturally it would just remain as lead-206. As I started to mention, excuse me, sometimes a single radioactive isotope can actually undergo either alpha or beta decay. As I said, there's no strict rule, there's no hard and fast rule about having too many neutrons means it's definitely going to undergo beta decay, too many protons definitely undergo alpha. They are generally following those guidelines, but sometimes they'll do different things. And sometimes one isotope can actually undergo either. For example, polonium-218 in the previous decay chain, in that uranium-238 decay chain we just saw, we wrote down alpha decay in the decay chain, and that is true for 99.98% of polonium-218 atoms. 99.98% of the time they will emit an alpha particle and become, going back, polonium in the middle there becomes lead-214. So that is true almost all the time, but very, very occasionally, 0.02% of the time, a polonium-218 atom will undergo beta decay rather than alpha decay. We can draw decay chains as a visual display. This diagram here on the vertical axis, we've got mass number. On the horizontal axis, we've got atomic number. And we've just got arrows that show the decay. So this is the uranium decay chain we were just looking at. It starts at uranium-238. You can see the atomic number of uranium is 92. The mass number, as we said, uranium-238. The first thing it does is undergo alpha decay. Alpha decay loses 4 from the mass number, so we're down to 234, and it loses 2 from the atomic number, so it goes down to 90, from 92 down to 90, and that gives us TH, which I believe is thorium, but I could be incorrect there. The thorium then undergoes beta decay. Beta decay, remember, is a neutron changing into a proton, so it doesn't change the mass number, but it increases the atomic number by 1. So we get it moving to the right by 1, and then to the right by 1 again for another beta decay, ending up at uranium-234. That undergoes alpha again, loses another 4 mass and another 2 atomic to get back to 230, and it's thorium again. That's alpha again, and so on all the way down. Now we're down to polonium-218. As we said, that can undergo either alpha or beta. Alpha is far more common, but beta does occasionally occur, so we want to reflect it in our decay chain. So we draw both. We draw the alpha decay down to lead-214, but we also draw the alpha decay up to 218 AT. I'm sorry, I can't recall what AT is. The chemists among you might already know. So we draw both on, and you'll see that that starts to occur quite a lot of these different branches. So there are actually a whole bunch of different pathways you could take. But regardless, you always end up at lead-206. We always end up with the stable isotope lead-206. So we've talked about the different types of radioactive decay, alpha and beta. We haven't talked about half-lives, and half-lives are the time it takes for that decay to occur. The decay is random. There's no way for us to predict it. If you take a single radioactive element or single radioactive atom and you watch it, there's literally no way for us to ever know when it will decay. Not possible. We cannot predict it. It is purely random. However, what we can do is measure how frequently radioactive atoms do decay and determine the average time after which half of some set of atoms will have decayed. So say you go and you take 1,000 of these of some radioactive atom and you watch them, and after 10 days you're down to 500. That 10 days would be your half-life. It's how long it took for half of those atoms to decay. We wouldn't normally do it with small numbers like 1,000 or 100,000 even, because remember, atoms are really tiny. We take really big numbers, big samples of these things. But that's all the half-life is. The half-life is just the average time for half of the atoms to decay. For example, cobalt-56 has a half-life of 77 days. If you take 100 atoms of cobalt-56 and you put them in a box, and then you open it 77 days later, 50 of them will have undergone beta decay and turned into iron-56, which is stable. The other 50 will still be cobalt-56. They haven't decayed yet. You close the box again, it's now got 50 iron-56s and 50 cobalt-56s. You leave it for another 77 days and then you come back, half of those 50 cobalts will have decayed again. now you'll have only 25 of them. The 50 iron 56s will still be iron 56, and you'll now have 25 more iron 56, so you'll have 75 iron 56 atoms. I'll just point out here that I'm talking about 100 atoms and then 50 and then 25. It's not very reliable with those sorts of small numbers. It's the same idea of flipping a coin. If you were to flip 10 coins, you would expect half to be heads and half to be tails, but it's pretty common that they wouldn't be exactly those numbers. It's pretty common that you'd get maybe 3 heads and 7 tails, or 4 heads and 6 tails, or so on. So small numbers, these sorts of averages aren't always going to be true, but remember that these samples of atoms are generally going to be huge, huge numbers of atoms, and the averages come out very close. For example, if you flip 100,000 coins, then you'd be very likely to get somewhere around 50,000 coins being heads. Wouldn't be exactly necessarily, but it'd be very close, and the variation would be pretty minimal compared to your significant figures and how precise you actually want it to be. So the numbers I've got here of 150 and 25, they're indicative and descriptive, but they probably wouldn't be exactly accurate if we were actually only watching 100 atoms. Calculating how many atoms are left after multiple half-lives is very useful. If you have one half-life, you'll have half of the atoms left. If you've got 2 half-lives, then you will have half of them decaying during the first half-life, leaving half still radioactive, and then half of that radioactive half will decay, leaving you with a quarter of your original number of atoms. This is something that is often trips students up, where they think 1 half-life, then 2 half-lives, and then they double the half-life again for some reason. But it only takes 1 more half-life to get rid of half of those that are left again. Right? It's always 1 half-life, get rid of half that are left. So you start with a whole, you start with 100%. After 1 half-life, you're down to 50%. Then after 1 more half-life, you're down to 25%. Then after 1 more half-life, you're down to 12.5%. So after 3 half-lives, you're down to 12.5. After 4 half-lives, you're down to half of that again, which is 6.25%. After 5 half-lives, you're down to half of that again, 3.125%, and so on and so forth. So I recommend taking a moment to think about that if you're not sure. You always just add 1 to the number of half-lives and halve the number of atoms that are left radioactive. There is a formula that can help you if you want to rely on maths rather than just thinking about it, and sometimes this can be useful if you have a non-whole number of half-lives. If you have N atoms, so big N, capital N atoms, of some substance that has a half-life of T half, so T with a little subscript half, then after some time T, we will end up with N final, the number of radioactive atoms that are left. This is not the ones that have decayed, this is the ones that are left, being the original number of atoms times a half to the power of T over the half-life. So it's a little bit of a complicated formula because we've got a power, an exponent that's not a whole number, it's a T over the half-life. So you rely on your calculator to figure that out, but you certainly can use this. If we're dealing with whole numbers of half-lives though, you don't really need to because it's always just going to be these percentages. Right? 1 half-life, 50%, 2 half-lives, 25, 3, 12.5, 4, 6.25, 5, 3.125. But if I asked you, for example, 2.5 half-lives, then it's harder to calculate how far from 25 to 12.5% is it actually going to go in that extra half-life. That's a bit harder to calculate, so use this formula and that will tell you exactly how much you'll have left. Also, the note there, because we're dividing the time by the half-life, they can be in any units. The time units will cancel out. So it doesn't matter what units you have your time and your half-life in, but they must be the same unit in order to cancel out. So if your half-life is in days, you can't go and put the time in hours or weeks. You have to convert it to days to make sure it cancels the units with the half-life given. There's an example calculation there. I won't read through that, but if you are struggling with that formula or you just want to verify how it works, feel free to follow through that slide. It's just the calculation using that equation. Some examples of half-lives. So how quickly do these things decay? Some of them decay very quickly. Hydrogen 7. Remember, hydrogen is a single proton, so hydrogen 7 has 6 neutrons. 6 neutrons are completely unnecessary. The proton isn't even repelling at itself at all, so no neutrons are necessary for hydrogen, but for some reason hydrogen-7 has 6 neutrons, and that is very quickly going to decay. That is very quickly going to decay, and without knowing what's actually happening there, it's very likely that one of those neutrons will decay into a proton and become helium, or there could be other forms of radiation beyond what we're discussing. But you could likely guess it's got too many neutrons, it's going to want to change them. Beryllium-8, 10 to the negative 18 seconds. Right? Actually, I can't remember if I said the hydrogen-7 decay time. Half-life is 10 to the negative 24 seconds. 10 to the negative 24. Right? That's a 1 in the 24th decimal place. That's how many seconds it takes for a hydrogen-7 to decay on average. Right? So half of them on average will decay in that time frame. So if you had 100 of them, then after 10 to the negative 24 seconds, 50 of them will already be decayed. After 2 times 10 to the negative 24 seconds, so twice as long, there'll only be 25% left. So 75 of them will have decayed, and so on. So very quickly, there'll be none left. Beryllium-8 has a half-life of 10 to the negative 18 seconds. Polonium, we're getting a lot slower, but still ridiculously fast at 10 to the negative 5 seconds. Oxygen-22, we're up to 2.25 seconds. Cobalt-56, as I mentioned already, was 77 days. And of course, you can get very long ones as well. Uranium-232 has a half-life of 68.9 years. Plutonium-242 has a half-life of 272,300 years. Barium-130, we're up at 10 to the 21 years. And tellurium, I think that's pronunciation, tellurium-128 is up to 10 to the 24 years. And that is, for your interest, 160 trillion times greater than the age of the universe. So tellurium-128 has a decay half-life that is very, very, very long. For a decay chain, each of those decays has a half-life, and we can measure those or look them up. So each step has a half-life, but for the decay chain as a whole, the term half-life will generally refer to the time taken for half of the original atoms to end up as final atoms. Right? So not for just half, so uranium-238, we're not talking just for half of the uranium-238 to decay. That's just the half-life for uranium-238. So that's just your standard 238 uranium half-life. For the uranium-238 decay chain half-life, what we're talking about is for half of those uranium-238 atoms to make their way all the way through the chain and end up as that stable lead-206. So that's what we're talking about for a decay chain half-life. For uranium-238, that decay chain half-life is 4.5 billion years. 4.5 billion years for half of those uranium-238 atoms to end up at the end of the chain as lead-206 atoms. Now, we already talked about this idea of transmutation, of forcing one element into another, and that we can do that in a lab, but it also happens naturally. Earth's atmosphere is constantly bombarded by cosmic rays, which are energetic particles. They are of multiple different types from out in space from various sources, but they commonly hit our atmosphere. And when I say commonly, I mean just constantly, all the time, right? Billions of times a second everywhere across the atmosphere. Just, you can't even count it, just too much. Right? So it's just constantly happening. And one of the things that happens when these cosmic rays hit our atmosphere is that a neutron can collide with a nitrogen-14 atom. And when it does that, that nitrogen-14 atom absorbs the neutron, and emits a proton. So it absorbs a neutron and emits a proton. So we still end up with the same mass number. We still end up with a mass of 14, but now we've gone from having 7 protons into having only 6 protons. So effectively, that atom has taken the neutron in and got rid of a proton. It's swapped a proton for a neutron, and it's become a carbon-14 atom. And this happens all the time up in the atmosphere. It happens a lot. So our atmosphere is full of these carbon-14 atoms. Carbon-14 still has 6 protons, just like regular carbon. Regular carbon being both carbon-12 and carbon-13, which are stable. They're not radioactive. But carbon-14 is radioactive. Because it is still just carbon. It's still got 6 protons. It still undergoes the same chemical reactions and processes as carbons 12 and 13. It will be used by plants to make carbon dioxide. Right? It will be used to create carbon dioxide. It will create carbon dioxide with other carbons and oxygens, which will be used by animals when they absorb that carbon dioxide. And they will then turn that carbon dioxide into things like sugars. As we already mentioned, plants turn water and carbon dioxide and oxygen, they turn it all into different sugars, different carbohydrates and things. And that means that some of those molecules will have carbon-14 in them, mixed in with all the carbon 12 and 13. Carbon 12 is the most common. It will have some carbon-14s mixed in with them. Carbon-14 is radioactive. So now we've got these molecules which have carbon in them, but it's a radioactive carbon. That radioactive carbon will undergo beta decay. The extra neutron that it took in is not quite stable, and it will at some point give off an electron and turn into a proton. And that will turn that atom back into a nitrogen-14 atom. Remember, it started as one, so it turns back into that eventually. It just takes a neutron, holds onto it for a few thousand years, and then eventually gives off an electron and turns it back into a proton and ends up back where it started. It's a different proton than it started with because it got rid of that first one, took a neutron in, and then a few thousand years later, that neutron turns back into a proton, and we're back to where we started with nitrogen-14. So we end up back with nitrogen-14. But the half-life for that process is around about 6,000 years, 5,730 years, but we'll often just say 6,000 for simplicity because we're often talking pretty imprecisely. We're just talking rough ranges. So we've got this half-life of around 6,000 years for the for the carbon-14 to turn back into a nitrogen-14 atom. Carbon-14 inside a plant is constantly undergoing this nuclear decay. Yes, it takes thousands of years for it to occur for a specific atom, but we've got so many atoms in us, as do plants and animals, that there is always lots and lots of these carbon-14 atoms decaying into nitrogen-14. So it's constantly happening inside us, inside plants, inside every living thing. While the plant is still alive, it's constantly absorbing new carbon-14 from the atmosphere. Remember, it's being created in the atmosphere from the cosmic rays. The plants absorb it, so they're absorbing more carbon-14. Some of their carbon-14 decays, but they constantly absorb more. And what happens is that we end up at an equilibrium of sorts. That the carbon-14 in the plant is decaying, but it's absorbing more carbon-14. And it ends up at it just maintaining a fairly constant level of carbon-14 within the plant. So a fairly constant percentage of its carbon will be carbon-14. So while a plant is alive, and that's the important point, while it's alive and still absorbing new carbon-14 from the atmosphere, then the amount of carbon-14 in the plant as a percentage of its total carbon will be around about equal to the fraction of carbon-14 in the air as a percentage of total carbon. So while the plant is alive, it maintains this ratio of carbon-14. Some of it decays, it absorbs new carbon-14. Once the plant dies, it can no longer absorb any more carbon-14. Right? It can't absorb any more, but the carbon-14 it does have will keep decaying at that rate determined by its half-life. Right? Around about half of the atoms after about 6,000 years. So it will keep decaying. So that means that we can come along and we can measure how much carbon-14 is in the plant, the dead plant, the remains of the plant, compared to how much there would have been when it was alive. And that will tell us how long it's been dead for. Right? If you get a piece of dead plant and you measure the carbon-14 radiation, the radiation coming off the plant due to carbon-14 decay, and it's only half of how much carbon-14 is in the atmosphere, that means that plant's been dead for about 6,000 years because half of it has already decayed. Right? If it's a quarter, then it's been dead for about 2 half-lives because 3/4 of it has already decayed. So in that process, you can tell when the plant died based on how much carbon-14 is left as a fraction of its total carbon. And that is the process known as carbon dating. So carbon dating is just monitoring the radiation that comes off an organic material that is now dead, and comparing it to how much carbon-14 radiation you would expect to come off it if it were alive, and that difference tells you how long it's been, how much has decayed, and therefore how many half-lives it has gone through. So this little diagram, which I presume I stole out of a textbook, although I can't honestly recall, 23,000, I'll say 24,000, I'll stick with my 6,000 rounded version. 24,000 years ago, we had a full amount of carbon-14 decay, the same amount as in the atmosphere. After 6,000 years, so we're down to 18,000 years ago, half of that has decayed, and we're left with half the amount of radiation that we had when we were brand new, when we were still alive. Another 6,000 years and half of that goes away, so left with a quarter of what we originally had. And then another 6,000 years, so this is 6,000 years ago, we have a half of that quarter, so an eighth of the original carbon-14 atoms there that are decaying. And now if we go and measure that, the radiation from this organic thing that died 24,000 years ago, it will be down to a 16th of that original radiation amount. And so that's how carbon dating works. We just see how much carbon-14 is left, and we do that by seeing what the rate of decay is, and we compare that to what the carbon-14 would have been when that thing was alive, and that'll tell us how long ago it died. Carbon dating is one type of what is called radiometric dating. Radiometric simply means using radioactivity as a meter, radiometric. And we're using dating because we're using it to determine how long ago something died or was formed. Right? So that's what radiometric dating means, and carbon dating is one type of that. Radiometric dating can be used to age all sorts of different things, but depending on the age of the thing, you'll want to use a different type of radiometric dating, a different isotope, a different element as your guide for dating. Carbon dating, using carbon-14, is only useful up to around about 60,000 years old, and as I said, only for organic material, organic matter that's taken in this carbon, plants from the atmosphere or other animals from the plants and eating other things. Okay. So it's only working for organic material, and it's only working for organic material up to around about 60,000 years old, because beyond that, beyond 60,000 years old, there is not enough carbon-14 left to give us meaningful results, to give us any kind of actual usable data. Remember that I said it's only useful, half-lives are only generally useful when you've got lots of atoms, because it's a rough average, right? Just like flipping the coins. If you flip 100,000, you're going to get pretty close to 50,000. If you flip 2 coins, you might not get any heads or tails, right? You might get both of one rather than neither, right? That, you know what I mean? So carbon-14, not much use after 60,000 years. But there are other methods. We have uranium-lead dating. Remember that uranium decay chain that turns into lead? We've got 700 million years or 4.5 billion years, depending on whether you're talking about the first step of the uranium decay or the whole chain. So you've got half-lives there. You've got samarium neodymium dating, which is 100 billion years half-life. Potassium argon has half-life of about 1.3 billion years. Rubidium strontium 50 billion years, and uranium thorium 80,000 years. So depending on what you're looking at, what kind of substance, how long the possible age ranges are, you can look at these different radioactive isotopes and compare how much of them there are now versus how much there would have been when it was formed, and figure out when it was formed. So that works for asteroids, for planets, as well as for carbon dating for living matter. So that's the end of this lesson, which, as I said, it was called the nucleus, but that's because all of this radioactivity comes from the nucleus. It comes from how many neutrons and protons we have in the nucleus and what the result of that force is. In the next lesson, we're going to keep talking about radioactivity, but we're actually going to talk about radiation in general and how it affects life and how it affects us, as well as we're going to come back to the nucleus a little bit and just talk about some even more dramatic ways that nuclei can change.